Okay, apologize for starting a few minutes late here. I had a doctor's appointment. I should have had plenty of time, but I know the medical community looks that way. So I was delayed, and so anyways, I got here. So sorry for the wait. That's what I was told as well. So domino effect. Anyways, we are at week 11. The 1st of November. So I will give you guys your take-home exam, but I didn't make it available yet, but I'll make it available on Blackboard probably tomorrow morning, okay? So you'll see it'll pop up under take-home exams. You'll see right now, you'll only see the midterm exam, but there's a folder that's final exam. I'm not quite done with that, but I'll make that available very shortly. So that'll be available tomorrow. If it isn't, someone email me and say, what are you doing? But it should be available tomorrow. So it's because it's going to be due November 15th, and our final projects, if nothing changes, are going to be due November 22nd. So what we were talking about last class, or what we left off on, was we were talking about forecasting. And forecasting, as you know, is trying to determine what will happen next. And what we use, past history is usually a pretty good indication of what is going to happen in the future. So that's one way we do forecasting. And specifically what we're looking at is time series forecasting. And there's a process we go through to do that. The process first is we recognize that a time series can have 4 components, okay? A time series can have 4 components. And the first one is long-term trend, okay? Long-term trend is, what is this doing over the long term? Like the general gist of where this thing is headed. It can be stationary. It can be, a positive linear trend or a negative linear trend. It can also be quadratic. It can also be exponential. But what is it doing over the long haul? That's the first component. And as statisticians, we're pretty good at recognizing that and using that in forecasting, long-term trend. The second one is does it have seasonal variation? So seasonal variation, typically things tied to the calendar. So my son is working his first job. He's 16. He works at a garage. And he said, boy, Dad, he's the tire changer guy. That's what he does. And he was slammed, last night, and he was slammed today. And I said, well, that's seasonality. He doesn't care what I say either. But I said that's because it's winter tire time, Lucas, and it'll always be that way. So we can always see seasonality. Not always, but a lot of things have seasonality, and we can see that, right? By graphically, we can see patterns that happen, often tied to the calendar. Now, the two we don't do so well with are cyclical variations, and cyclical variations, are just that. They kind of are economic variations. If we're in a recession year, likely maybe sales will be down, not necessarily because of what we're doing, but hey, the economy is down. Depressions, growth, those kind of things. It's cyclical. It changes just because we function in an environment like the economy. And last one is the worst one for statisticians to predict is random effects. Random effects are just randomly things happen, right? Just I think I used the example, the bingo bus pulled up and wow, our sales went off the charts. So statisticians don't like that. So the first thing we need to do before we use a technique is try to understand, what our time series looks like. And what we try to determine is it stationary or does it have trend, long-term trend? And how do we do that? There was a couple methods we used to do that. What did we use to do that? What do we use? What's one way we could do that visually, I guess? We could graph it, right? And we showed like a scatter diagram with the lines, and we could see that. So one way we can determine that is we can graph it, but a graph is, a picture and it is subject for interpretation. Like I might see it as, I look stationary to me, and you might say, no, I think there's trend positive, and someone else might say, no, I think there's trend negative. It's subjective for the most part, right? The picture graph can be subjective. So we want to put a number to it, and we used a couple things to do that. What were the numbers that we used? There was one method I showed you, and then another method that I showed you that the book espouses, and it's probably more of a correct method, but what do we use to determine if it had trend or not? Yeah, we added a trend line, a regression line, and a couple things we looked, like the slope of a line, the general format of a line is y is equal to mx plus b, where m is the slope and b is the intercept. And we looked at the m, and if it wasn't very big in relation to the points, we're saying, that's pretty flat, right? There's not much slope to it. And further, we looked at the r squared value, which is known as the coefficient of determination. And that tells us the percentage of the movement of the y value, so whatever we're graphing, that we can determine or explain by movement of the x value, which in this case is time. So if that's a low value, we're saying, time isn't driving this thing. Time is not the thing that's driving this. So low values there indicated stationary, higher values indicated linear trend. And the book method, which I don't care which one you use, I want to show you both because the book is actually probably a little more mathematical, a little more correct, was to use regression. And what did we look at when we looked at regression? What do we look at to determine? Because when we did regression, we were actually doing a hypothesis test to try to prove that the slope was not equal to 0. That's what we're trying to prove. The slope is not equal to 0. So what do we look at to see if there was evidence to support that claim? Yeah, the p-value. And a p-value, I know you saw this in other courses or even undergraduate courses. The p-value is the probability that if I make this claim, that I'm wrong, that I've committed what we call a type 1 error. If I make this claim, that I'm wrong. So lower p-values, mean more evidence to support this claim. So typically we look for p-values less than 5%. If we see a very small p-value, we say, hey, there's a lot of evidence to support the fact that this slope, is statistically significant, that it matters, that it has long-term trend. So that was a lot of work just to determine, hey, what are we seeing here with this trend? And we said, all right, when we identified, if it's stationary or linear trend, that determines, what we can do, how we can graph it. And I think there were 4 techniques we used for stationary. What was the simplest one, the first one we introduced, which a lot of people may use this in a manufacturing environment or a sales environment. They may use this. It's simple, it's easy, really doesn't take any math. What do we call that?
Last period technique.
Yeah, the last period technique. So we just look and say, hey, what was it last week? That's our forecast for this week. What was it last month? That's our forecast for this month. That's a valid approach. Now, that only looks at one period, so we can also use moving average. And it depends, maybe a 3-week, a 3-month, a 5-month, 5-year moving average. You see this all the time. So we take the last so many periods and average them together. There's also the weighted moving average. And the weighted moving average recognizes that things that happened more recently are probably more important than things that happened less recently. So it puts weights of that. The weights have to sum to 1. The weights have to be descending. And the last one we used was exponential smoothing. The big strength of exponential smoothing is it uses all the values, and it has what's called a smoothing constant, alpha, which determines how much of the weight goes toward the actual value and how much goes toward the previous forecast. And in essence, where that weight is either smooths or makes that forecast reactive. And there's 2 techniques for linear trend. We only really focused on one because it's kind of the dominant one. What is the dominant one? The dominant one that is useful not just for forecasting, but in a lot of situations where we're trying to say, hey, I need a function that takes this value and ports it to this value. What do we say is the most dominant thing we use in forecasting. Linear regression, or just regression. And you could teach a whole. Actually, you could have a series of courses in regression. That's how powerful that tool is, and we cover like a half hour of it. So linear regression, and the other technique that we really didn't talk about, it might have been in your homework, was something called Holt's technique. And Holt's technique, if you will, is kind of a sister to exponential smoothing, in that it has a smoothing constant alpha for the stationary, and it has a beta constant for the trend. But that kind of was the method we used, and we said, all right, well, that's kind of crazy that you want one forecast, but if it's stationary, you have 4 methods, and if it's linear, you have 2 methods, and there's other ones out there. But we want to choose the best one. And what do we do? How do we assess that a forecasting technique was good or not so good? What could we look at to assess if a forecasting technique was good or not so good?
You could use it, but on the data you already have, the old stuff that's happened, and see how well it fits with that.
Yeah, very, very good. So, we may be at, I don't know, year 10, or maybe month 120. We'll look at it that way. But we can go back and say, well, I know what month 56, 57, 58 was. If we use this technique going backwards, how good would it have been, right? So we call those performance measures of forecasting technique. And a couple that we looked at was like mean absolute deviation, was called the MAD. Like on average, how far off has this estimating technique or this forecasting technique been off historically, the average absolute deviation? Or the mean absolute percentage error, the MAPE, like as an absolute percentage, how far off is this technique been? So what's kind of great is I can forecast something, but I can also say, historically speaking, how good would this technique have been in the past? So that's kind of like last week in a 15-minute nutshell. So let's do at least one of the homework questions, and all these came with data. So I don't know. Let's do. Unless you guys have one specifically you want to do, let's just do 21, 22. I don't know if that leads into 23 already. Yes, it does. Okay, so let's do 21 through 23, unless you guys have a specific question. So this is Burger Barn. So Pat Young, manager of the Burger Barn restaurant in Logan, Utah. Is interested in determining an optimal inventory for autofocus for frozen French fries. The number of pounds of French fries used by the restaurant over the past 15 weeks is as follows. 15 weeks. So graph this time series, verify that it is stationary, and then let's just do that first. Okay, so I'm going to go back to my PC, go to material by chapter. I'm going to go to chapter 7, and this is problem 21 and 22. I'm going to get my data, open that up in Excel. Since it's in compatibility mode, and I'm using 2016, I'm going to upconvert that thing so I have all the features and functions of Excel. Now let's graph it. So I'm going to highlight the data. I'm going to say insert. I'm going to go to scatter, and I'm going to pick the scatter with straight lines. So visually, and it looks nice. I guess it looks all right. I'd probably want to graph this thing. I'd probably want to, give it a better title and all those good things. I would also want to add a trend line. So I'm going to right click on it, add a trend line, linear, display equation on chart, display R squared value on chart. And I'm thinking it's stationary, but after I add the trend line, boy, I'm almost positive it is, because we see a couple things. My values are like 16,000-ish to 14,000-ish to looks like 18,000-ish. But my slope here is only 9.2, so it's pretty insignificant when we figure out the values. Plus, my R squared value is 1/5 of 1%, which is telling me that time isn't driving this thing. The percentage of the movement of the Y value determined by the movement of time is very low. If I also wanted to verify this statistically using regression analysis, I could do that. I could do data analysis, regression. My Y range would be B1 through B16. My X range is time, A1 through A16. There are labels in the first row. New worksheet ply. I'm not going to look at any other options. And it comes here, it tells me that p-value, the p-value is the one I want to look at. The weak one says 0.875266. So it says if I make the claim that that slope is non-zero, basically the p-value is saying there's an 87% chance that I'm wrong. I don't want to make that claim, right? That's a bad deal. So there's no evidence to support that it's not stationary. So I think I've determined, through a value, various methods, that this thing is stationary, right? And it doesn't hurt that the book next asks me to use a 3-week moving average, which I know is considered a stationary technique. So that kind of validates it for me as well. So instead of me doing it, I know that in Blackboard, if I can find Blackboard here. Is that my LinkedIn? Whose LinkedIn is that? Must be shows. More LinkedIn. So under Chapter 7, there's a forecast template. So I'm going to open that up. And it says it wants to use a simple moving average, 3 weeks. So let's take the data. I'm going to take that data. Oh, you guys can't see this. Someone tell me that. So I'm going to copy that data over to my forecasting technique, and I'm going to paste it in the simple moving average. Number of periods in moving average, well, I think it asked me to do 3 first, and we have 15 periods worth of data. So using this, it's telling me my forecast for week 16 is 16,366.67. It says, how about if I use a 4-week moving average? So let's change that. That'll take the last 4 weeks. It says 16,475. And then it asks me which moving average gives the lower mean squared forecast error. I don't like the mean squared forecast error. Let's look at I like the MAPE, mean absolute percentage error. That makes sense to me. Like 4-week moving average, we're off about 5.5%, right? That makes sense. I can communicate that. If we use the 3-week moving average, I'm off about 5.1%. So even though it's not a huge difference, which moving average historically has been better, the 3-week or the 4-week moving average? Using the MAPE anyways. The 3-week moving average has historically been better. That it was 21. It says, so our forecast for week 16 is 16,366.67. What's our forecast for week 17? Kind of a trick question because it is also, it's the same, right? Because if we're saying this thing is truly stationary, we're saying week 16 we're going to forecast 16,366. Week 17 the same thing. Week 18, we're saying it's stationary, right? It's oscillating around something stationary, so it would always be that. It's saying, what is the forecast? So consider the data in problem 21. Suppose the exponential smoothing is used. So I'm going to take this same data. I'm going to copy it. Let's go over to the exponential smoothing tab and paste it. And we have 15 weeks worth of data. And it says using smoothing constant of 10%. Okay. Looks like that MAPE is 5.14. Uses smoothing constant of 0.2. 5.20. Looks like it gives a little worse. Gives the lower mean absolute value. It just tells us to look at some other ones. And finally, I'm going to move on to 23. It says, all right, it looks like 0.1 is better than 0.2. And 0.3, it looks like it's kind of between there. I could try some different ones. 0.05 looks even better. 0.9 looks worse. But instead of me doing trial and error, what can I use to try to pick the best smoothing constant? I can use solver. So if I go to data, solver, I could say I'm trying to, in this case, I'll pick the MAPE, which is J3. I'm trying to minimize that by changing variable cells. The smoothing constant, subject to the constraint. The smoothing constant, which is E3, has to be less than or equal to 1. And make unconstrained variables non-negative. I'm going to click solve. I hate this one because if you do it, you may have got a smoothing constant of 0. And it does minimize the MAPE at 4.95. But all it's saying is, well, 16,400 was the best. And that was the first value, like period 1. So in this case, it kind of gives you a weird result, right? Smoothing constant of 0 is kind of a weird result. Now, did anyone get a different smoothing constant when they solved that? Anyone else get a different smoothing constant? No? What also happens with these, okay, is remember what solver is doing. It's doing a trial and error approach. And when it gets close enough, it says, hey, I'm done. And it stops. So sometimes where you start matters. I started at 0.9. If you would have started at like 0.1, you might have got a different value. It's going to be close, but it's not going to be exactly the same thing. Okay. So any issues with that? Any questions with that? Let's see. What else did I assign? Let's do 30 as well. Okay, that's the gateway computer one. And I'm going to do that a lot quicker. But let's make sure we go through one like that. So this is save later. Did I assign you guys 30? Yes. Did I give you the data for it?
It's the same as 31, 32.
Oh, it's the same data? It is?
It's down.
It's down further? Oh, right here, okay. Okay. All right, so I didn't give you the data, I'm sorry about that. The 30, yeah, I think it is different than, all right, so you do have to kind of take it off the solution. So I'm just going to take these 40 data points, I'm going to paste them into, oops, paste them into a blank. So this is sales in thousands of dollars at getawaycomputer.com over the past 40 weeks has been as follows. So week 1, $238,000 of sales. Week 2, $251,000, so forth and so on. I want to take a look at this and statistically validate that it has some trend to it. So I'm going to highlight that data, insert, scatter, and I'm going to do the smooth lines. Boy, and just visually looking at this, I can kind of see, hey, that's trending upwards. Let's right-click on it, add a trend line, add display equation on chart, display R squared on chart. And I'm also seeing a lot of evidence here that it does have a positive trend. So the slope is 5.5, but the R squared value, 99.12. So 99% of this movement of this is based on what? It's based on time. Let's go a little further. If I do data analysis, regression, my Y range would be B1 through B40. My X range is A1 through A40. In this case, I forgot that I didn't copy over the labels, so I'm going to uncheck the labels box. I'm going to click OK. And for our X variable, which that doesn't have a label because I didn't copy over labels, it just tells me X variable. We see that p-value is 1.04 e negative 40, which means 1.04 times 10 to the negative 40th. So it's 0.39 zeros, 40 zeros, I think it is, 39 zeros, 1.04, which is a very, very small number. So what we would say is there's overwhelming evidence to say that this thing has a non-zero slope. So, you know, no matter how you slice it, this thing has trend. Okay, this thing has trend. And in fact, if we use regression analysis, which we've kind of already done here, you know, when I look at this, this is my regression analysis. So that equation, y is equal to 5.45 plus 242.39. That is my regression equation. So if it was asking to predict week 41, how would I predict, or is this month? Yeah, this is week. If I was predicting week 41, you know, what would I use? How would I predict the sales for week 41? Just using that, we'll use the template in a second, but yeah, plug 41 in for the X. And if I was predicting week 42, there should be an X here. 42, I would make that X 42. And if I was predicting week 43, and it's different. Why is it different? Because, hey, we're thinking this thing has trends, so we're thinking it's going up by a factor of, basically, I think it was in the thousands, about 5,500, right? 5,500 every week. If we use, and I think that's what they've done here, if we use this, okay, we use this, it's doing the same thing. You see it's every week, 41, 42, it's about 5.5 different. One of the total sales over the 13-week quarter, what do we have here? 41 through 52. That is, what, 12 weeks in that quarter, 41 through 52. So we sum those up, but it also wants what the forecast is for 53. So plug 53 in here. You know, if I went week 60, I could plug in 60 and it gives me that value, but we want 53. So it looks like what they've done is they summed those 12 weeks plus, you know, whatever it is for week 53. But the total sales over the quarter, excuse me, are 6.4 million. Okay, because that's in thousands. So 6.4 million is our forecast. Now this is because there isn't much variability in the data, and we saw that, you know, there wasn't much variability. There's not much skew off that line. If we look, we have an incredibly low MAPE, right? Mean absolute percentage error is 1.46. 4%. That gives me some information, I could tell my boss, not only is this my forecast, but historically, if we use this technique, we'd have been off about 1.4%. So that's pretty good, right? If you can get a MAPE, truthfully, if you can get a MAPE under like 10%, mean absolute percentage error, that's pretty strong, right? If you can say, once where I had no knowledge using this technique, I can give you a forecast that's traditionally been off about 10% either way. That's much better than making a forecast with no knowledge in the dark. Okay. So were you guys able to do this homework, understand what we're doing here? And I think this is one of those things that we cover in this class that everyone has a need for this, right? Everyone forecasts, and maybe your X variable though isn't time, right? Maybe you try to relate like, well, I don't know, the number of amount we've spent on advertising, is that related to sales? So your X value, your independent variable might be advertising, or it might be, is the size of the home related to the price? So your X variable would be size, and your Y variable would be price. Or temperature, is that related to the sales of your ice cream stand? So your X variable would be temperature, your Y variable would be sales. So this can be used in a lot of different situations. All right, any questions? All right. Then let's move on. And we're going to move on. We're going to move up a chapter. And I'll introduce this topic, and then we'll take a break, and we'll come back, and we will we'll do the techniques. Okay, so chapter 9, we're going to talk about queuing models. And what is a queue? Not the letter, but the Q-U-E-U-E. What is a queue?
A line.
It's a line, right? So who'd be concerned with queuing models? What kind of organization, what kind of business would be concerned with queuing models? Sure, like if you think about it, a convenience store, the doctor's office, right? The airport. I'm concerned with queuing right now. It's advising week where undergraduates come. I have 40 advisees. They come, they make an appointment with me. We talk about what classes they'll take in the spring, and they leave, right? So I'm operating a queue right now, right? So many business applications are concerning queues, okay? So queuing is the study of waiting lines or queues. What we're trying to do is design a queuing system that enables organizations to perform optimally according to some criteria. For example, if I am a convenience store, we're going to say the time of service is, how long they spend in the queue is very important. If we are a medical office and we are a very niche operation, maybe we're trying to maximize the number of patients we see. We're not really concerned with their convenience, but we're concerned with the number of patients we might see and how much money we might make. So maximum profits, desired service level, all these are things that we want to look at. So analyzing queuing requires an understanding of the service measurement. And the things we're going to get from our measurements from a queue are some measures that will help us understand what's going on. Things like the average time a customer spends in line. That would be important to me, right? If I'm trying to make sure that's under a minute, because I know through some studies that at a minute, people get frustrated and they determine they'll never come back, that's important. The average length of the waiting line, like how many people are in the waiting the probability that someone has to wait. All these are things that we're going to be able to measure. So if we think about a queue, it's really like three things, okay? So first, customers arrive some way into the queue, okay? So some way they come to the queue, and we're gonna talk about that. Like, are they deterministic? For example, when I do advising, I try to make it deterministic, the arrival pattern. So I do that by scheduling appointments, right? Like, you come at 1, you come at 1:15, you come at 1:30. So I say 4 per hour. I try to make that deterministic, yes? So we try to, it can also be probabilistic. So for example, maybe we average 10 customers per hour, but maybe sometimes we get 20 and sometimes we get 1 per hour. So it could be probabilistic, and we'll talk about the different ways that people arrive or things arrive in a queue. So there's different ways we can wait in a queue, and we'll talk about that, like queue configuration. There are queues, like, for example, where everyone waits in the same line, and then there might be multiple servers. I think a lot of banks operate this way. I don't go to banks anymore. But you wait in the same line, and then whatever teller becomes available, you go to that teller, right? Or, if you think about a grocery store, I do go to grocery stores, they have multiple service areas and multiple queues, right? So you go to line 13 or line 7 or line 8, because you're saying, I'm going to wait in this line for this service area. There can be what we call multi-stage queues. So go to the emergency room, they do like a triage on you first, and then they determine, like, if you are really bad, or you can wait in the waiting room for 3 hours, right? So that is one queue you go through, the triage, and then another queue you go through. If you go to the airport, there's multiple queues there. There's a security queue, and then a queue to get on the plane. You guys know what I'm saying? So we can have, different configurations. The way we serve people in a queue can be different. First come, first serve is typical, but maybe a queue does, last come, first serve. So we have to consider those things. And then as they arrive, customers have, different service patterns. Okay, so that can also be deterministic. For example, if I was a machine, an advising machine, maybe I say I advise everyone. It takes me exactly 10 minutes to advise every student. But that's not the case, right? Maybe if I'm an assembly line, right, that's going to be deterministic. We punch this hole. We can do 60 of these hole punches every second. Every second we do 60 of them, right? It's deterministic. But it can also be according to a probability distribution. And we see more of that, more so in like retail and restaurants than ever, because there might be an average. Maybe on average it takes me 10 minutes to advise a student. But some students have their act together, and maybe it takes me 3 minutes, and then some students, let's just say, don't have their act together, and maybe we end up talking a long time about a lot of things in our life, and maybe it takes 30 minutes, right? Think about the doctor's office where I was just at. They try to make this part deterministic, right? They try to say, we're scheduling appointments every 5-10 minutes, but they don't know, how long that service is going to take. It's not, maybe some person takes 1 minute and some person takes 20 minutes, right? So it's not homogeneous. So we want to understand those elements so we can get to these performance measures, okay? So I'm going to skip ahead a little bit and talk about some terminology, and then we're going to come back, okay? So we'll talk about arrival in a bit. We'll talk about that after break, and we'll talk about service after break. But what I want to talk about right now is the queue configuration, like the waiting line characteristics, okay? Factors that influence how we would model a queue. And we're going to talk about line configuration, jockeying, balking, priority, all those good things. So I've already kind of mentioned this. Line configuration is important. We can have a single service queue, meaning, everyone gets in the same line because we only have one server. So it's just one line, one server. That's a single service queue. We can have a multiple service queue with a single waiting line. That is the bank example, right? We have one line, but we have multiple service queues. So you wait one line, but there's multiple tellers. We can multiple service queue with multiple waiting lines. That would be an example of the grocery store, right? Every checkout counter is a separate service queue. We can also have tandem queues, which I mentioned, like the airport, the emergency room, are examples of tandem queues. We also can experience different behavior in waiting lines, and it kind of throws us off a little bit. Jockeying occurs when customers switch lines once they perceive that another line is moving faster. So it's kind of when we have multiple service lines and multiple servers, it's kind of a self-regulating thing, which is good, right? If you've ever been you're in line 13, you say, whoa, it looks like line 12 is moving faster, so you jockey. You leave line 13 and go to line 12, right? Sometimes you're right, sometimes I'm always wrong, but sometimes it happens. Balking occurs if customers don't join the line just because they think it's too long, it's moving too slow. So they want to join the queue, but they balk at it, right? That happens in queuing models as well. Balking says, hey, I perceive it to be too long, I'm going to come back another day, or I'm never coming back, which is the worst thing for us. But I'm not going to ride that ride if we're talking about Disney. Priority rules talks about how the next customer is selected for service. Because we are humans and we have a sense of fairness and justice, typically things that serve humans, are first come, first serve. Especially if they require the same type of service. But there are some things that make sense to do, like last come, first serve. Not maybe makes sense, but it happens. If I'm grading exams and you stack up a pile of exams, I pick the one on the top. Well, that was probably the last one in, but the first one I grade. Yes, that happens. Sometimes in computer queues, that also happens. Estimated service time. Maybe we do the things that take the shortest amount of time first. Random selection of customers. I don't think most people would like that. If you went to the deli line, instead of it going sequentially, I would like it because it's kind of like a lottery. It puts a little fun in your day. But most people would not like that, but we have that. There's also priorities based on the emergency room example. For example, the people that have the most severe injuries or problems, they get to go first. Okay, so but priority rules are a component of queues. Tandem queues, multi-server systems. Customer needs to visit several service stations, usually in an order to complete the service process. Patients in an emergency room, passengers prepare for the next flight. We've talked about that as well. Another characteristic we talk about is the homogeneity of the queue. A very homogeneous customer population in which customers require essentially the same type of service. An assembly line is a very homogeneous queue. Everything that comes through it needs, this bolt tightened, right? The same damn thing. We talk about advising that might be different. Someone might need a minute, someone might need 30 minutes. Banks, they actually try to, if you're doing a simple transaction, you can do that with the teller. If you want to talk about your life insurance and your family goals and your retirement planning, well, then we're going to ship you to that other queue because it's not a homogeneous type of service that the teller can do. So we're going to shift you out. So homogeneity is something. And in many business situations, the service process differs, and we're going to talk about that. So we kind of dealt with the middle here first because that's more terminology than anything, but what we're going to talk about when we come back is customers arrive at a queue according to some pattern. The queue has some configuration, whatever it might be, and then the things in the queue are served according to some pattern. So we kind of talked about the middle. We're going to take a break and talk about the ends. And that's really what we need to analyze for us to be able to come up with performance measures for this queue. So it's 7:21. Let's come back around 7:30 and we'll we'll move on. Okay, so yes. So I should have erased it, but we talked about like the characteristics of a queue. I said after break we're going to talk about the arrival process and the service process. So I'm going to kind of go back in the slide, slide 5 here. And there are two possible types of arrival processes. The first one is deterministic arrival process. So this is, the assembly line. Stuff arrives one every second. Or, I tried to make my advising deterministic. So a student shows up every 15 minutes to my office. Doctor's appointment. The more likely situation, if we think about like the retail environment, the restaurant environment, a lot of different things, is a random arrival process. A random arrival process means, it occurs according to some probability distribution that is much more common in the business world. And typically, when we think about it, there is one model that this works with more so than anyone, and it's called the Poisson process. And there are 3 characteristics for it to be under that process. One customer at most will arrive during any time interval. So you're saying, well, that doesn't make sense. I could walk in with my significant other and there's 2 people arrive, but if you slice the time interval small enough, you don't exactly arrive at the same time interval. For a given time frame, stationary. For a given time interval, the probability of arrivals with a certain time interval is the same for all time intervals of equal length. That's in a given time period. So obviously, we're going to have more likely have more customers at lunch hour at a restaurant than we would at 2 p.m. In independence, the arrival of one customer has no influence on the arrival of another. And we know that's not the case as well, because if the bus driver decides to stop at Arby's, well, so do other 48 other people. So all these things are kind of violated in real life, but still it is the best way to model a lot of things. And that is the probability distribution for the Poisson arrival process. But really all we need to know, okay, to be able to use this, because we're going to use Excel to do this, is lambda. Okay, that symbol there is lambda, and that's the mean arrival rate per time unit. So if I say 10 customers per hour arrive to our restaurant, that is lambda, or a customer per minute. That's what lambda is. Now, if we look at this, let's look at an example. This is Hank's Hardware. Hank's Hardware, customers arrive at Hank's according to a Poisson distribution. Between 8 and 9 a.m., an average of 6 customers per hour arrive at the store. So lambda is 6 per hour. We want to know what is the probability that 0 customers come in the next half hour, like 8 to 8:30, right? So we got to first adjust our lambda. So if it's 6 customers per hour and I'm looking at a half-hour window, what does my lambda look like? If 6 customers per hour, what's my average in a half-hour window? Okay, very good. So our lambda is going to be 3. Now, how do I use that? Well, I think it shows that adjustment over here. But let's go into Excel and just do this. Okay, so let's pull up a new workbook, a new blank workbook in Excel. And let's throw in column 1, let's throw K, where K is the number of customers. And let's throw in column B, P sub K, so the probability of that many customers. Fancy Excel style. Okay. And let's do, let's do 0, 1, 2, and I don't know, let's go down to, let's highlight that area and go to drag, and it should recognize that, hey, you're trying to fill a sequence. And let's go down to, I don't know, 20. So it should put 0 to 20 in there. So if you just 0, 1, and it'll recognize, and then highlight 0, 1 and go to the corner and drag down, it'll recognize you're doing a sequence, and it'll autofill that. Okay. So the function I'm going to use is, crazy enough, equal Poisson, and I give it 3 things. I give it the x value, meaning the probability of that value. So in this case, I'm going to give it A2 because I'm looking for the probability of 0 customers coming. I give it the lambda, or the mean, and if I'm talking about a half hour and it's 6 per hour, I'm just going to plug a 3 in there. And in this case, I'm looking for point probability. So I'm just going to do false because I'm not looking for cumulative probability. So A2, comma 3, comma false. It tells me the odds that I don't get any customers in the next half hour is 5%. Now, if I drag this down, it tells me the odds of all these things. So the odds that I get 1 customer is 15%, 2 customers is 22, 3 customers is 22, 4 is 16. Remember, 3 was the average, so it kind of peaks right around there at 3. 5 customers is 10%, 6 customers is 5, and then it starts going down. You guys see that? I could even, if I wanted to make this even more general, I could put lambda over here, and I could make it a variable, so let's just throw in 3 there. And I could go back to my original equation, and instead of hard coding the 3, I could point to E2, or E1 I guess it is. And I know I'm going to drag this formula down, so what do I want to do with E1? Because I don't want it to change. I want it to always be E1. What do I want to do with it? I want to absolute it, so let's absolute it by using the F4 function key. And I drag that down, and obviously it's going to stay the same. But now if I say, well, what if I say I'm talking about an hour, and 6 customers per hour is the average, so I change my lambda to 6. Now the odds that I get 0 customers is 0.2%. The odds that I get 1 customer is 1.4%. The odds that I get 5 customers is... So this is kind of, if you can kind of look at this, I could... Okay, so I'll show you this, it's kind of neat. If I highlight B2 through B22, go over to conditional formatting. There's a lot of neat things you can do with conditional formatting. But one thing I can do is data bars, and then pick, pick gradient fill and pick a color you like. And it kind of shows us, you see the value in that bar is how long the bar, value in that cell determines how long the bar is. So you see the highest ones, 16%. All I'm trying to show you here is the shape of that distribution, right? So it kind of looks like this, and it has a long tail, right? So that is the most common distribution of, and many things, especially in like how customers arrive, especially human customers, occur according to this distribution, right? So that's the main one we're going to work with. And that has value in itself. What we just did has value in itself. If I understand my average, I understand that it comes in as a Poisson process. I have now the ability using that function to figure out, if I average 6, what's the odds that I'm going to get 3 customers in the next hour? What's the odds that I'm going to get 4 customers or 4 or more? And I can do that math. Does that make sense? Yes? Okay. So let's talk about, then I'm going to skip ahead here, and I'm going to talk about the service process. And the service process varies as well widely among customers, even my advisees. Even though I try to make it deterministic, some advisees take 3 minutes, some advisees take a half hour, medical appointments, banking appointments. So when service time varies, and a lot of times it does, it is also treated as a random variable. And the service process is a little different than the arrival process. It most frequently is modeled as what we call an exponential distribution. And the exponential distribution, that's the equation for it. You don't have to know that. But it kind of looks like this, where the probability that service time is completed within these many units. So it looks like this, and it's a different kind of equation. But all I want you to know, we're not going to really do any math with this. All I want you to know is that exponential is the most common. Okay, and we're not going to do the math for that one, but let's just leave that alone for now. Okay, so we talked extensively about the queue has characteristics. Customers arrive according to some process. Typically, it could be deterministic, but a lot of times it's random, and that's Poisson. They're served at some random process typically, and that's usually exponential. So what we want to do now is we want to start measuring these queues. And before we start getting performance measures of a queue, we have to understand a couple things about a queue. First off, we can only measure a queue when it has achieved steady state. So what is steady state? Well, steady state is when a queue is like operating well. When things are churning along. So when isn't a queue in steady state? So the first time a queue is not in steady state is a lot of times in what we call the transient period, like when a queue first starts up, right? Like a good example of this is my barber. He opens at 8 a.m. and when he opens the door at 8 a.m., there's usually like 4 old men waiting to get in, right? So in that 5-minute window, he gets 4 customers, right? Because they're waiting to get in. That isn't like normal operation. That's a crazy period. You know what I'm saying? That's called a transient period. And it's hard for us to measure that because the queue is not operating correctly. Initial transient behavior is not indicative of long-run performance. So these performance measures are really not applicable to that period. The other thing, so steady state follows that period, but the other thing that we have to achieve steady state is the effective arrival rate of the things in the queue must be less than the sum of the effective service rates. So for example, if things are arriving at 5 per hour, but I'm only serving them at a rate of 2 per hour, well, things are just gonna explode, right? Things are coming in faster than we're serving them. That queue will never achieve steady state. So it says the effective arrival rate must be less than the sum of the effective service rates. So if things are arriving at 10 per hour, and I have servers that can handle things at 6 per hour, how many servers do I need at least to achieve steady state? 2, right? Because if I just have 1, the queue's never going to operate properly, right? Things are coming in faster. Now that happens sometimes, even in operating queues that are well, but for us to measure it, it needs to be in this thing called steady state. All right. So transient period, steady state, I think you guys understand that. Here are the things we are going to measure. These are the measures that we're going to get from queuing analysis. The first one is P sub 0, and P sub any number is the probability that there are that many customers in the system. So P sub 0 is the probability that there are no customers in the system. And let me explain the system to you. So what's the difference between the system and the queue? So I have maybe 2 servers, okay? And they have 1, 2, 3 customers. This one's waiting on a customer, this one's waiting on a customer, and this one has a customer in line. So at this point, these people are in the queue because they're waiting in line. All of these people, though, are in the system, right? These are the servers. This is the service area, I guess. So if I looked at this, I would say in the system we have 1, 2, 3, 4, 5, 6. That's the bigger part. And in the queue itself, in the queue part, we have 4, right? So the system includes waiting in line and being served. The queue just includes the waiting in line part. So if we look at L, so P sub 0 is probably there's no customers in the system, meaning no one waiting in line, no one being served. P sub 1 would be probably there are 1 customer in the system. So probably that person, if there's only 1 customer in the system, will probably be being served, right? Yes. L is the average number of customers in the entire system. So that means waiting in line and being served. L sub Q is the average number of people in the queue. That's waiting in line. So they're different, right? L is the whole damn system. L sub Q is the people just in the line, the average number of people waiting in line. W is the whole system, average time a customer spends in the system. So that includes waiting in line and being served. And W sub Q is the average time a customer spends just waiting in line. P sub W is the probability that arriving customer must wait. And then this little symbol down here is rho, R-H-O, Greek letter rho. It stands for the utilization rate of the servers. So it's a percentage from 0 to 1. It's the percentage of time that a server is serving someone. So that's important because there's some places we want, like a grocery store, we want our checkout people to be busy like a lot, right? Like 95% of the time. Maybe in a bank, when we're talking about maybe a customer service rep, maybe we don't want that person to be busy 99% of the time because maybe they have other things to do. Maybe they're making sales calls or doing some accounting. I don't know. But maybe 99% utilization rate is too high. Okay. All right, so let's talk. I know it's a lot of front matter before we get to the math, but that's how queuing works. So the way we classify queues, we use 5 things. And we denote it this way. We use slashes. So the first part is the arrival process. So how do things arrive according to my queue? If they are deterministic, we use a D here. Meaning like it's scheduled like, hey, 1 every 15 minutes. But typically it's more of a random process. So we use an M, which you're saying, why don't we use a P because isn't that going to be Poisson? Well, no. Poisson is a distribution under a class of distributions known as Markovian. So when we see an M here, and that's what we're going to see most of the time, what that is telling me is things are arriving according to the queue, according to a Poisson process. So the first thing is how they're arriving. The second slash is how we're serving them. So once again, that can be deterministic, not really, not typically. It can be Markovian. Markovian, believe it or not, is also the family for the exponential distribution. So the ones we're going to be dealing with most of the time are MMQs, which means a Poisson arrival process, which is a Markovian family distribution, and an exponential service, which is a Markovian family distribution. The third thing is the number of servers. So if you want to think about it this way, how many tellers do I have? How many customer service reps? How many grocery store checkout people do I have? How many professors do I have advising? Whatever it might be. Those 3 we always have. We always have to have these 3 things. So if I have a Poisson arrival process, an exponential distribution, and I have 3 servers, I have an MM3Q. Okay, those are the 2 things I'll always have. These last 2 things are I don't want to say optional, but a lot of times we assume them to be infinite. So this one, if we have it, is the system size limited? So if we think about a bank queue, you might say, well, Dr. Miko, that system is not limited. You can't put 1 million people into the branch up here in Loretto. You're right. However, does the size of that system ever become an issue for that queue? I don't think it does, right? So we can assume it's infinite. Not an infinite amount of people can fit in the Walmart queue, like the grocery queue, but does it ever become that? We can assume that it's not a limiting factor. Now, if let's say I had a call center and I had 10 lines only. Well, that is a limiting factor, right? Only 10 people, maybe we don't have no holding. Only 10 people can be in that system at any given time, right? So that is a limiting factor. So I would have to denote a 10 there, okay? Most of the time, this isn't a factor we have to consider. The system size is not a factor we have to consider. We just assume it to be infinite, all right? And the fifth one as well, we typically assume this to be infinite. It is the population size. So it's the things that can enter my queue. And I know there aren't an infinite amount of things that would want to go to the branch in Loretto, but we have to assume that it's not limited. If I am tasked with fixing something on aircraft carriers for the United States government, we probably have 4 of those. There's only 4 things that can ever enter my queue. That's it. Right? There's only 4 things. So that is something I need to factor in. There's not an infinite amount of aircraft carriers. There's not even 10, there's not 50, there's 1,000. There's only 4 aircraft carriers. I'm guessing the United States government has, maybe it's more. But there's only 4. I was just reading some of the time. I think there's only transatlantic cables under the ocean that transmit data. I think there's only 312 of those. So they said every 3rd day one needs to be fixed. So there's like that's probably an instance of where the system size is limited. There's only 312 of those underwater data cables. You guys know what I'm talking about? Like fiber optic cables. I guess that's a point of vulnerability for us in our internet, which we depend on. So anyways, that would be something I would have to factor in. But most cases, we assume these to be infinite. And when we do that, we just leave them blank. We don't even talk about them. There are cases where those do become an issue. Okay, but the first ones we're going to talk about, they're not. All right, so we have to classify the queue, and then you're going to like this, that we use a template. So I think I put that up there. So this would be a crazy queue. This would be MM61020 would be a queue that things arrive according to a Poisson process. They are served according to an exponential process. We have 6 servers. There's only 10 things that could ever fit in my system at any given time. And there's only 20 things that could ever enter my system, that would ever want to enter my system. That would be an MM61020 queue, but that's kind of a crazy queue that we don't really have to worry about. So what are we dealing with a lot of cases? Well, a lot of cases we're dealing with MM, like plain old MM queues, with MM with a number. So an MM1 queue, let's do one of those first. An MM1 queue is a Poisson arrival process, an exponential service time, a single server, potentially infinite queue, an infinite population can enter it. So there's some pretty high-end formulas, but we're not going to use those formulas. We're going to use a template, but let's look at an example and apply that template. So Mary's shoes, customers arrive at Mary's every 12 minutes on the average. So it's giving that to us according to a Poisson process. It's giving us to an inter-arrival time. So it says 1 customer arrives every 12 minutes. Now what I'd like to do is I'd like to make that a rate per hour. Okay, I want to make that a lambda. So I want to say how many per hour. So how do I get there? Well, if it's one customer every 12 minutes, my lambda, an hour is 60 minutes. So I've set up as a ratio. I'm going to cross multiply. 60 times 1 is 60. 12 lambda, divide both sides by 12. I get lambda is equal to, customers are arriving at a rate of 5 per hour, right? If one every 12 minutes, you probably could have done that in your head. One every 12 minutes, 5 per hour. That makes sense? It's telling us service time is exponentially distributed. That's why it's MM, right? Poisson, exponential MM, with an average of 8 minutes per customer. Okay, so 8 minutes per customer. So we can serve one customer every 8 minutes. And we use lambda for the average for the arrival. We use mu for the service. So how many in 60 minutes? Well, once again, cross multiply 60 equal to 8 mu, divide by 8. We get 7.5. So we can serve at 7.5 an hour. So we only have one server, so this is good. They're coming in at a rate of 5 per hour, but I'm knocking them out at a rate of 7.5 per hour, which means I can achieve steady state. Does this make sense? Because I'm knocking them out faster than they come in. Management is interested in determining the performance measures for this service system. Okay. So we're going to go to Blackboard, and we are going to go under Chapter 9. And under Chapter 9, we're going to go to Queue Template. And open up the Queue Template. And you'll see this workbook has multiple tabs. And the one we're primarily going to focus on is the MMK tab. So MMK, which means Markovian, and K servers. And we need to give some inputs here. So first off, lambda. Well, things are arriving at 5 per hour. We're serving them at a rate of 7.5 per hour. Based on that, because these are formulas that are pre-programmed in here, which you don't need to know, but I would like you to see this. If we have an MM1 queue, we want to look at this row, because we have one server. So if we had 2 servers, we'd look at this row. So let's go through these performance measures. L is the average number of people in the system. On average, we have 2 people in the system. L sub Q is the number of people waiting in line on average. On average, we have 1.33 people waiting in line. W is the average time they spend in the system. It's 0.4. 0.4 what? 0.4 hours, because I plug these in hours, so all the times will be in hours. So 0.4 hours, 0.4 times 60, roughly 24 minutes, right? So they're spending 24 minutes in the system. The average time they spend waiting in line is 0.26 hours, or roughly a quarter hour, or how much? 15 minutes. The probability that someone has to wait, about 2/3 of the time they have to wait. Mary, since she's our only server, is busy about 2/3 of the time. That makes sense because we have an MM1 queue, so Mary is busy when someone has to wait. These are the P sub zeros. The probability of no one in the system, 33%, which makes sense since Mary's busy 67% of the time. Probability of 1 customer in the system, 2 customers, 3, 4, 5, 6, 7, 8, 9, 10. So if we use these measures, we could, if you think about it, we could do a what if. What if we hire 2 people? What if we hire 2 people? So what does that change? Well, a couple things that changes. Now, how long do people have to wait in line on average? Wait in line. What's that? 0.016 hours, right? So I would multiply that by It's probably a little bit over a minute or something like that. If I multiply that by 60, it's not much at all. Probability that someone has to wait is only 16%. Mary and the other server only busy 33% of the time. The average number of people in the system is 0.75 because we're getting them out faster. All those good things are coming into play. So, this can be, very powerful analysis. Let's do another one. And I want to look at, I'm going to skip ahead here. And I want to skip to, we'll come back to those. I want to talk about this, economic analysis of a queuing system. So, why in that previous example would I not necessarily say, well, geez, let's see, people are waiting 15 minutes on average. Let's go with 2 servers. Why might I not do that in the business world?
The cost of having the second server.
Okay. So what goes down is the waiting time, and there is a cost associated with that, right? There's a cost for your customer to wait in line. It's kind of hard to measure what that cost is, but we want to try to estimate that. So, the performance measures previously developed are used next to determine a minimal cost queuing system. The procedure requires estimating costs such that, and it's hard to do. Hourly cost per server is pretty easy to do. We know what we pay people, right? That's an easy thing to do. The thing that's hard to figure out is the customer goodwill cost while waiting in line and the customer goodwill cost while being served. So what is a goodwill cost? What does that mean, a goodwill cost? Sometimes, I think, I brought up goodwill. I banked a lot of goodwill with this person or this person. But what's goodwill cost? What does that mean? What would that mean? Okay. Very good. So if you think about it, it's kind of hard to assess that, right? So if you think about it, if you go to, I don't know, a Lexus dealership, right? And you have to wait around, you're getting ignored, and you leave there, well, that might be a considerable goodwill cost then, right? It's hard to measure, right? You didn't buy anything, you didn't know about you, but if you would have bought something, right, it's kind of a lost opportunity. Disney does this very well, right? Disney tries to assess, because when people go to Disney, it's the time of their life, blah, blah, blah. But what are the things that they complain about? What are the 2 things they complain about? Lines, that's probably number 1, right? How long they wait in line. What's the other one? Cost, yeah, that's cost. The web sometimes the top right. Okay, so those I can see. So I refresh again. Right? So, anyways, so why are those 2 broken out? There's a goodwill cost while waiting in line, goodwill cost while being served. Why are they broken out?
Get to the actual thing if you're stuck waiting for.
Yeah, while we're being served, we might be mad it's taking so long, but we're narcissistic people, so we're at least glad the attention's on us, right? They're not serving Sarah, they're serving me. So the goodwill cost while waiting in line is typically, a factor of 3 or 4 times higher than the goodwill cost while being served. You might be unhappy it's taking that long, but you're more unhappy when what? When you're waiting in line and they're serving Nathan, right? You're not happy to see that. So we need to factor that in. And if you think about it, a lot of places try to do things, like the medical doctor I was just at, I got to give them credit, like at least in magazines, like I read Time, I think I told you, spent some time reading, so that was good, right? Sometimes they try to entertain you to reduce that cost. Disney, they send like Goofy over to talk to you, right? So that reduces that stuff. But they're trying to reduce that goodwill loss. Yes, they are. And it's more important in some businesses. If you're a convenience store, if you're Sheetz, and convenience store is your the way you make a living, that goodwill cost. If you have to wait, every second counts. They really look at this. They do a lot of queuing analysis at Sheetz. So let's look at this. This is an old example, but I guess it's a timely example since Thanksgiving is coming up. Wilson Foods has an 800 number to answer customer questions. If all the customer's representatives are busy, when a new customer calls, he or she is asked to stay on the line. The customer stays on the line if the waiting time is not longer than 3 minutes. I'm not going to talk about that right now. So on the average, 225 calls per hour are received. I don't know if it says it, but that is, it's a Poisson arrival process, so it's an MMQ. Lambda is 225 per hour. An average phone call takes 1.5 minutes. So that's a one call per 1.5 minutes. So I want to get that to a mu of 60 minutes. So I'm going to cross multiply. 60 is equal to 1.5 mu. So that means mu is we can handle 40 per hour, okay, per server. So if I look at that, I know how many servers do I at least need to have to achieve steady state. If 225s are coming in, every server can handle 40. We need at least how many? 6. We need at least 6 to achieve steady state to measure this. Okay. So what are the other things coming to line? Okay. Well, we talked about that. A customer service rep is paid $16 per hour. So let's write that. Our CSRs are paid $16 per hour. That's important. Wilson pays the telephone company 18 cents per minute. So this is the line charge, like when someone's in our system, that's costing us money. So 18 cents times 60, 0.18, that's per minute times 60. 18 cents, I keep typing the wrong numbers. That is $10.80 per hour. That's the line charge. And let's see, we have estimated, and this is customer goodwill cost while on hold is $20 per hour. And customer goodwill cost while in service, I don't know if it's saying 5 cents per minute there. Okay, $3 per hour, I think it's saying. Maybe that's 12 cents per minute. 20 cents per minute, so that's what it's saying. 20 cents per minute, so $12 per hour. That's goodwill cost in line. And 5 cents per minute, or $3 per hour. So it's a factor of 4. That's typically what they use. Goodwill service. Okay. So let's use that same model. And we're going to go to the queuing, and we're going to change things up a little bit. Lambda, we said is 225. We said mu is 40. And you notice, first thing you notice is I didn't get any values at all for servers 1, 2, 3, 4, 5. Why? Doesn't achieve steady state. Now, on the top right, you'll see some values we can put in. The server cost is $16 per hour. So if we hire 6 servers, makes sense. $96 per hour, 7 servers, $112 per hour, 8 servers, $128 per hour. The goodwill cost when waiting. So when waiting, while they're waiting, they're actually assuming both the 1080 charge, that's the line charge, and the $12 charge. So that's $22.80. And the goodwill cost while being served is the $10.80 plus the $3, so it's $13.80. And if we look at that cost, it's gone up. Okay, so now this is factoring in the average number of customers waiting per hour, average number of people served per hour, and it's calculating out a total cost with the server rate. Now, if we look at this, so if I hire 6 servers, we're not turning them out fast enough, so we're assuming a lot of goodwill loss and some line charges as well. We go down to 7 servers, our total cost goes down, even though our salary goes up because we're turning things through faster, our goodwill loss cost is going down. We go to 8 servers, it goes to $220. kind of bottoms out there. We go to 9 servers, it goes up to 227. And once it bottoms out, it's going to continue to go up. Why? What's occurring there? So it starts at 458, 235, 220, goes to 227. It'll continue to go up. What's occurring there? Right. Is seeding the gain we're getting from reducing the waiting time, right? So that's what's happening there. So that is, if I asked you what the optimal number of servers to have here, you would tell me what? 8. Okay, 8 servers. Now, as a textbook question, these aren't so bad to do. In real life, it's really, really, really hard to determine goodwill loss, right? It's really hard. You think about St. Francis, when a student enrolling here, might mean, I don't know what we make per student, depends on the student, but an MBA student, might mean, $15,000, $20,000 or whatever. I don't know what we make on a MBA student. So, the fact that we didn't get back to you an email. There's a big, or something that I was rude to you. Dr. Meek was rude to you, and you went somewhere else. Something like that. It's hard to assess those things, but they can be significant. So some industries have better standards for that. Convenience stores. There's some industries that don't care about that so much. I'm not picking on anything, but if it's monopolistic, if it's like Department of Transportation, Department of Motor Vehicles, I don't think they care so much that I have to wait in line for my driver's license picture. Where else am I going to go, right? So the goodwill loss, okay, he's not happy, but what's he going to do? Write your congressman, right? There's not much they can do. So that's kind of a low goodwill loss. All right, so I will. Well, let me assign a couple of these homework. We're not done with queuing analysis. We're going to have some time. So I will put up the take home tomorrow. Next week, we will finish queuing analysis. That's 11/8. And we have some extra time. So we'll review for the exam, obviously. You can have some time for your group project. But there's probably some other things I'm going to show you, some things that aren't in the course that I think are neat in Excel. Might give you a little flavor of that. But anyways, for homework for tonight, I guess, for this week. I'm not going to give you all these, but just this. A handful of them. I would like you to do do number 1. Do number 2. Don't do 3 yet. Don't do 4 yet. Do number 5. Don't do 23. And do 24 A through C. Don't worry about D. 24 A through C.